Thanks for coming today. Yes, H2O Driverless AI is our flagship product, and it's doing well in the market, and it's a lot of change every few weeks or months. When we talk to people, there's new stuff to announce. So today I'm going to present the slides, the introductory slides from H2O AI World in London that we had a month ago. And since then already lots of things have changed. H2O is a machine learning company. That's all we do. So there's nothing else we do than machine learning products. We write software and our users use it. There is open source and there's closed source. And H2O-3 is the product that's the open source version. That's the platform on which you can build scalable machine learning models up to terabytes on even Spark systems with sparkling water. So unlimited size, super fast training, accurate models. We have deep learning, we have gradient boosting, we have random forest, we have linear models, we have unsupervised methods, clustering, dimensionality reduction, anomaly detection, all kinds of things. So that's H2O-3. And today we're talking about Driverless AI, which is the proprietary version that takes it another step further, where it actually makes feature engineering for you. And feature engineering, if that's not a term that you're familiar with, is creating new columns for the data set. So when you have a data set, you have usually, let's say, a big Excel table, right? 100 million rows, 100 columns or something. And now we just make extra columns from those existing 100 columns. And that's the art of feature engineering. And usually when you have domain knowledge and you do this feature engineering right, you can get a huge lift in your model's performance. So for example, if you want to predict the outcome, let's say, is the salary of a person, right? And all you have is their job title and their zip code. Then that alone is very hard for a model to just memorize, because every zip code and every job title in combination, it has a different salary. Sometimes they have multiple of these. So you can just predict, let's say, the mean of all engineers in Palo Alto, right? And that's a prediction. But maybe you can do something else. Maybe you can say, what about only people in this zip code with 2 kids and 4 cars or something, and you find the mean of those people, but you don't include yourself in that mean. So for every person in the data set, you put in the number that you compute from everybody else in a similar situation to you, and that gives you basically an estimate that's an out-of-fold estimate. And that's what's called a good feature, right? Because it's a very valuable number if you can compute that from the data set, and you're actually leaking, if you want, the target column Y into X, the matrix of the features. And that is an art, because if you do it wrong, you're going to have a lot of problems, because you put the answer into the data and then you're just going to overfit and you're going to cheat basically yourself, and nothing's going to work. But if you do it right, by doing this carefully with out-of-fold estimates and so on, where you do not take your own number for your own prediction feature, then suddenly you get a much better model. And those kinds of things are the tricks that the Kaggle grandmasters use. And there's only about 100 in the world that are Kaggle grandmasters. Kaggle is a website, as you know, that Google acquired that's doing nothing but data science competitions online. And we have 6 of those 100 grandmasters working for us here at H2O, right? And that's a real joy for us, because they know what they're talking about. You don't need to explain to them what is an out-of-fold estimate or anything. They know, right? They come here, they already know. They've done 100 competitions. They won these. They know exactly what the mistakes are. So when they show up, they just basically tell you what to do, what is missing in the product, how to make it better, and so on. And they can also code, because Python is, of course, something that they master. So and when we write a product like Driverless AI, we write it in Python, and we're using C++ and CUDA and all that as an engine underneath, but the actual algorithms are controlled from Python, which means everybody that knows Python can help, which is great for the company, because now we can have 50 contributors and not just 5. If you have to do something like distributed C++ or something, that's much harder to get a huge team to work together. So with Python, it definitely is easier. So this was a year ago when we got the Editor's Choice Award and then the Technology of the Year Award with Driverless AI. So basically, we were really able to create good models out of the box without any human interaction. And you might say, well, anything that just does a fit is good enough. Well, sometimes you can get 2 or 3% improvement by just doing this extra column generation, this feature engineering out of the box. And so to some people, this 2 or 3% improvement matters a lot, especially if you do fraud prevention or something. If you can reduce your fraud from 90 million to 80 million a year, then that one model was worth 10 million, right? And there definitely are companies that have that kind of scale of benefit if they apply AI properly. So AI to us is something that's smart about how it deals with the data. And the data doesn't have to be images or text only, can be, in our case, it actually cannot be images. We do not handle images yet right now in driverless AI. It only handles strings, text, let's say some fields with like description, like a tweet or something, or a document, then a number or a categorical. For example, like your gender or the type of car you drive or how many kids you have and so on. Those kinds of numbers. So it's a big Excel table if you want. It can be hundreds of gigabytes, but typically I would say it's in the order of 1 gig to 10 gig or something. That's like the sweet spot. And it actually then takes this data set, enriches it, and tunes hundreds of models with hundreds or thousands of extra features that it makes, and it will figure out the right combination of this enrichment and the fitting of the models. And it even will make an ensemble of models at the end, and then make a deployment package that is called the scoring pipeline that you can take outside of driverless to productionize your model. So for example, there is a Java version that's completely standalone, pure Java, has nothing to do with Python, nothing to do with C++. It's a pure Java runtime that does the same thing that the thing did that was displayed on your computer when you were training it in driverless AI. So a one-to-one mapping of the model that we fitted in Python, but then mapped into Java. And we're working on a C++ version as well. And then also, of course, we have a Python version that you can import into your Jupyter notebook to make predictions. And these are all standalone, so you don't need to have driverless AI in that same instance where you want to import that model that was previously trained in driverless AI. So driverless is basically the platform where you can train stuff, and then you take it outside and make predictions. This is the architecture. It looks a bit complicated at first, but you can imagine in the middle is just the training brain, and you can connect to it from the bottom left there, either with a Jupyter notebook or just with a web page. Like it has a browser built in, basically a web server, so you can connect to the port just like H2O-3. You connect to a port and then you see a website. And that looks like this. So this is me connecting to port 80 that we then map to this port 54321 inside that web server. So now it looks like a website, but actually it's driverless AI. And this is a listing of the data sets. I can also list the experiments. I can list other things. If I have done any of these other things, I can go to messages and it shows you that version 142 is out. And these are the new things that are added to it. It's hard to read here for the audience locally, but basically we have support now for IBM Power for this version 142. So everything is compiled both for Linux systems or for Power systems. We ship it as a Docker image or as a native RPM or Debian package, so it runs anywhere. Or on Power, of course, whatever it has to be to make it work on Power. It's probably also an RPM package. And then the improvements in this case were various, but I mean, there's always something, right? You can read the release notes. You'll see what's going on. I'll do a demo of this later. I'll go through all these points. We have enough time today, but there's a lot of installation guidance, key features, what's going on. There's all these different versions. The change log here, let me scroll down. This is November, this is October. A lot of changes. September, TensorFlow, LightGBM, XGBoost, GLM. All these things have been in for months. Support for compression, some support for data ingestion from, let's say, Google BigQuery, from Minio, from S3, from Hadoop, from Parquet files, for example. We have support for Snowflake, Redshift, you name it, basically. Whatever you want to import, you can import. KDB. So the data goes into the system, you tell it what to do, which usually is just go and fit a pipeline, not just a model, but a data engineering pipeline that does have models in it to make predictions in the end. And when you're done with it, then you can deploy it either using pure Java or Python or soon C++, as I mentioned, or you can even have these embedded scoring systems where we basically spin up a service where you can just post HTTP requests and you get an answer, or even a binary protocol where you can send thrift messages saying give me the answer. And this thrift protocol, of course, is then auto-generated for all kinds of languages, so you can send your C# request from a C# client that wants to know how to score a certain model. So when you run this on a data set that was in Kaggle 2 years ago, Kaggle has this competitions, right, where you have 2 months to compete, and at the end you see if you're good or not, basically. And while you're making these submissions along those 2 months, you can see on a public leaderboard how you're doing on a special piece of the holdout data. So they're telling you on a random third or something, you don't know which third, but on a third of the data on the test set, you're doing this well. But at the end, you'll take the other 2/3 to score. So no matter how well you're doing on that third, doesn't mean that you're going to do well on the other 2/3. So the real moment of truth is at the very end when you get scored on the other 2/3, and that nobody has seen that 2/3 before the answer. You just saw the data, but not the actual answer. And so the challenge now is to throw it into driverless, the training data, let it run, and at the end you give it the test set and say predict for that, and then we submit the whole thing. Kaggle looks at these secret 2/3 of it and says this is how well you're doing. Okay, that's the idea. And when you do this today, you get to 10th place. Out of 3,000 people that competed, out of the box, you're now 10th. And this is a data set where feature engineering mattered a lot. You need this 8-way interaction of these categoricals. So how many kids, how many cars, which zip code, what income group, what this and that. And then once you have that interaction, that like subgroup, then for those people, are they gonna need help or not with this claim management process or not, right? So there was some kind of binary outcome related to those categorical features, high cardinality features, but also numeric features, just a regular Excel table if you want, but one where they interact a lot. And you could say, well, a neural net can figure that out, or XGBoost alone can figure out the interactions, but it's not quite right. If you throw this into a regular algorithm like TensorFlow, you'll get a 45 log loss. And if you throw it into XGBoost, you might get 44.5 or something. But if you throw this into this system, you get a 43 or even below 43. So it's not a huge difference, but it's significant enough to make money for those who care. And that difference gets you basically 2,000 positions higher in the leaderboard. Because everybody can fit just a neural net out of the box, let's say. But not everybody can make these interactions explicitly and compute these out-of-fold estimates of those groups. For each group, basically, there's an outcome, right? So for every group, compute me the outcome for everybody that's not in this particular group. So it's a concept to get used to, but once you get used to that kind of stuff, it helps a lot. Now, I ran the same experiment here. It's still running. Okay, it's about to finish up. So I started this about an hour and a half ago, and it ran through all these iterations. So on the left, you see this chart that the yellow stuff is going lower and lower. So this is the error in log loss. Log loss says how well do I get the probabilities right for this prediction that says yes or no. If you say yes and it's actually a no, your error is 30. So if you did this wrong, for every single point, your log loss would be 30, huge. That's the mean log loss, right, for all these rows in the test set. In this case, actually, the number is measured on the training data internally. So we're measuring the performance on the one data set that you gave us by making our own splits internally to figure out how well we're doing. We can't just say fit on everything and here, good luck to you. We have to say fit on 2/3 or something, and then on the other third, we say how well we're doing. And we do this over and over again on different 2/3 to get an idea how well we're doing on this data set. But let's say we have this data set, we make predictions. If we got every probability of yes or no of 0, 1 just perfectly right, the log loss would be 0. But now we're having a log loss of 0.4. So that means the error in the probability is relatively small, but this number can go up as the logarithm goes down. So if you know the logarithm, it goes down really fast, right? And it goes down to infinity, down negative infinity, but we cut it off at 30 typically in machine learning. But as I said earlier, if you totally get it wrong, the log loss is 30 because it's negative of the log, where the log is supposed to be a zero crossing, which is where it is 0. The log at 1 is 0, right? So the log goes up. So you want to be at that point. So if it's a yes, you want to predict a 1. But if you're predicting a 0, then you have an infinite error. And so basically, where is the log 0.4? Well, it's about, I don't know, at 90% or something instead of at 0.9, roughly speaking, on the chart, if you think about it. So we're roughly off by 10% on average in terms of probability. But the actual number is either 0 or 1 always, right? So that means 9 out of 10 times we get it right, roughly speaking, and 1 time we get it wrong or something. You can make your own like rough guess of how well this does, but it usually helps you to have an intuition for what does it mean 0.4 of log loss if you're a data scientist. But 0.4 is a pretty good log loss, and 0.45 is also not bad, and 0.43 is just slightly better, right? So if you only want to predict something like, is this fan gonna blow up in my face next year or not, it's not that important that you get the probability perfectly right. As long as it's more than 0.3 or so, you're gonna get scared. But if you have to do this on a systematic fashion where you have millions of transactions and you wanna really figure out which of those are important, then you care about this last digit. So what this did is it made these features. I know you can't read this here, but this says out-of-fold mean of the response grouped by 4 columns. So we take these 4 columns, let's say age, zip code, income group, and age group. And of course, we compute income group and age group automatically from those numeric categories by binning them and so on. Then that 4-way interaction has a mean outcome. And that number is computed for 5 different buckets. And then for each of the 5 buckets, we use the other 4 to compute it. So we substitute their actual 4-way interaction, we make that into a number and put that as a new column in the data set. Okay, so enough about feature engineering. That's just one of them. There's many others. You can do clustering, you can compute distance to centroids, you can compute the dimensionality reduction, you can do the spinning that I mentioned, you can have other models making estimates, and then you use that as an input. You can have simple difference or ratio between columns. And of course, we have to figure out which of these interactions are important. How do you know? How do you know which group to make here? Well, it's all driven by the algorithm itself. So it figures out what columns matter, and then it does more stuff with those columns. So it's kind of a smart way to explore the space in a way that's not super greedy. So we don't want to exploit everything that we can see, but we want to still explore the space. So there's a balance between exploration and exploitation. There's a genetic algorithm at work. You have all these yellow points. At any given moment in time, there's multiple yellow points. That means we have something like 8 individuals in this race, and half the race horses at every step die because they're worse than the other half and get recloned with a small mutation, if you want. And now they're not just randomly created with a random mutation. Sometimes they can learn from each other. So if some race horse is better than the others always, then we can make more of those. But we want to still mutate them a little bit to give a chance to get even better. And there's also some randomness at play, something like you would say Monte Carlo, of course, but it's just a random number generator used at various places for some statistical tricks. There's also reusable holdout, which tells you how well you're doing on a holdout set. So if you have a third that you hold out, you build the model on 2/3 of the data, then you make a prediction on the 1/3. You're not just going to compute one score and say, okay, my log loss is 0.45 on that third. That's not enough. You want to measure many times on subsamples of that third. What's the log loss on those subsamples? And then you have a distribution of log losses on that subsample. That gives you a much better estimate of how you're doing on an unseen data set than just one number. So only if that distribution shifts significantly between models on that third holdout, then we can say, yes, we found something that's actually better. And that's when we make a step down in that chart on the left. So these are all systematic changes that actually are significant. And they also have an error bar. You can't see this from here, but there is an error bar with every yellow point. So we know we got better, and we are currently putting the final meta learner together for this ensemble. So there's an ensemble of, I think, 3 times 4, maybe 12 to 18 models. I'm not quite sure how many in this case. I didn't look up the numbers. But there's going to be something like a 4-fold or 5-fold cross-validation model. And we do that 3 times. 3 different XGBoost and light GBMs get blended together, and they each have a 5-fold cross-validation schema so that they can optimize the parameters again, so they have some unseen data in which they can tune themselves. So you can see there's a lot of logic going into this thing that is data science expertise that does it all automatically for you. And when it's done, that model will be very predictive because it is tested to be doing well out of fold on this kind of data set that looks like the training data set. Now, if the training data suddenly changes, next month it's all spring versus fall or something, campaigns, they change totally, then you might need a new model, right? So you would have to measure this model's performance on a new data set and see if it's still good or not, and if it's not good, you have to retrain. And we're not currently doing that yet in the GUI, so the GUI doesn't have this facility to help you with that, but that's coming soon. I will show you what you can do when this is completed. You can also see the GPU usage, the gains, the lift curve, precision recall curve, and that was the ROC curve. So this is the place where we have the best F1 score. And here you can see the confusion matrix associated with that. So there's a way to go through different thresholds. What you don't yet have is the ability to say, fix this threshold as a threshold that you want to designate for this model. And when it then makes predictions, it uses this threshold to make labels. So normally when this binary model makes predictions, it gives you a probability for class 0 or class 1, right? They add up to 1. But now we say, well, it's your problem to figure out what the threshold is so that you can say if it's a yes or no outcome, because we just give you probabilities. And once you say, okay, my threshold should be 0.75, as what you can see in this position here in this chart, where you like the true positives, false positives, true negatives, false negatives. If you like this confusion matrix at that point, then you would say, okay, this is my threshold. Every threshold has its own confusion matrix. Once you pick that threshold, 0.75, then every probability above 0.75 means yes to you. And we currently don't make that for you, that transition to the labels. We just say it's probability 7, it's whatever it is, probability 0.9. It's your problem now to figure out that this is supposed to be a yes. So we let you deal with the probabilities. But in a future version, you should be able to select from the GUI, freeze this threshold, and when you then make predictions, it knows that it should use that threshold. Does that make sense? Is that a feature that people require or request, or am I the only one assuming that would be useful? Does anybody have feedback? Is anybody here dealing with binomial models on a daily basis? Anybody doing machine learning on a daily basis? Anybody eating pizza on a weekly basis? Yeah, awesome.
Yeah, doing machine learning a lot of time.
Mm-hmm.
I like H2O, yeah, but kind of expensive, right? Oh, sorry.
Yeah, I do like H2O Driverless AI. Yeah, it's very easy to upload the data and to run automatic, right? Run the model and generate code and deployment. Yeah, but yeah, it's.
There's a free version for academic use. If you're at a university, a student or a professor, actually have Sven here who might be able to say more if you're interested, but there is a totally free version for academic use.
Okay, good.
So if you promise not to use it for commercial use and you have some affiliation with an educational facility, then that means you have driverless. So what you can do, you can look at the data set with details, and you can inspect the data set. You can look at the rows, just the standard like preview, right? So you can see that the data set is what you expect it to be. Oh, there's a question?
My question is more in the algorithms underlying. Are you using like its implementation based on supervised, unsupervised,
Yes.
and more on the storage side of things, like the data? How, because I use ML, I use ML for anomaly detection.
Wow.
And we store our binary compressed data on the servers, essentially in our data centers. But then there's a lot of latency. You download the data, unpack it, uncompress it. So how does H2O AI deal with that? Thanks.
Yes, thanks for the question. So the first question about unsupervised versus supervised, we have both. We have clustering, truncated SVD. We have different unsupervised methods, but we don't make just unsupervised models available to you. You only get supervised models right now. So we use unsupervised to make a better supervised outcome. For the supervised models, we have XGBoost, LightGBM, TensorFlow, GLM, and the rule fit, those 5 models. And usually the gradient boosting models, XGBoost and LightGBM, are the most predictive ones for these kinds of tabular data sets. Once you have images, you would need neural nets, which we don't have right now. But once you have text here, then you can actually have text columns. You can have multiple text columns in your 100-column data set. And for each of those text columns, we can either make TF-IDF like count-based features, statistical features, or we can also make TensorFlow, convolutional neural net, or LSTM-based features, right? So we have TensorFlow built in, and we use that for text columns. And then once you have that feature converted to a number, then it becomes a feature for XGBoost, let's say. So we do these kinds of unsupervised or supervised techniques to mix up the model to be as predictive as possible, but it's always a supervised end product. Now for the data ingest, you see here there's a file system, upload, Hadoop, Amazon S3, Google Cloud Storage, Google BigQuery, Minio, Snowflake, and KDB, and Redshift is coming soon. So we have some ingestion capabilities. If you click on Amazon, you just immediately get access to all kinds of stuff in Amazon. But of course, this system is running on Amazon, so if you click on this, it's faster than if it was running on Google's, and then it has to convert across and all that. So it's always about where you put your data. Normally for banks, they have it on-prem, and then the data is also on-prem, maybe on the same machine, or maybe a NFS or something that's close by. I would say the data size is usually in the gigs or tens of gigs or hundreds of gigs at most. And if you have a reasonably fast file system, the upload time is still slower, or less time than the modeling time, right? Modeling will take longer. Another thing we have, you can click on a data set and you can say visualize. So this will build a unsupervised exploratory screen that tells you everything that's interesting about this data set. And you don't need to do anything, you just need to wait for this to finish. And what it does is it aggregates the data first, which is a way of clustering it, but it it basically keeps the outliers alive. So it's something like a small epsilon environment around every point. And if you have neighbors that are close to you, you'll just gobble them up. And if you don't, then you're alone and you remain alone, but you'll still be in the data set. So in the end, you have a bunch of epsilon bubbles left that are all actually actual points. They're not centroids. They're not like the center of mass, right? If you do clustering, you have 2 points. The center of mass is in the middle, which is not an actual point. But here, these representatives or exemplars are actual points. So if I gobble you up, then I remain where I was originally. So there's always going to be a set of actual points left. And this aggregator is implemented in data table. Have you heard of data table in R? We're now making a Python version of data table. So we have both data table main authors for R and Python in the company, and we use data table a lot for feature engineering and munging. And so this is something that we use the C++ backend that's controlled from Python. So right now we have a unsupervised display of this data set. We never had to provide a target column. And you can click, for example, on outliers. And it will show you only distributions of columns for which there are outliers. So V6 has 3 outliers. You can click on those, and a point might actually contain multiple outliers, because this was the point of these three points are in one exemplar. So this is the actual 3 points that are weird in this V6 value. And this V6 value is 20. But everybody else is smaller than 20. See, this is 20, everybody else is up to 5. So you now know that there's something interesting in this direction. And you didn't have to do anything. It's not like Tableau where you have to manually plot everything. Here it plots you only what you should see. And the same for missing values. You see there's a lot of missing values in this data set. Lots of interesting distribution. This is a heat map. We'll do more interactive stuff for this AutoVis, where we can zoom in and out and, color by certain things, group by. A lot of cool visualization is coming up soon. This is just the first version, but it's a very useful tool to just quickly get a check of your data. So this one here is finishing up. It's probably scoring right now on the test set, making predictions. And yes, and this prediction I can now download and submit to Kaggle. But we won't do that today. I'll just show you how it works. But I'll show you like an experiment from the beginning. Okay, so I'll go to file system. I have a server here that has a local file system. I can import, let's say, this credit card data set. Of course, you can do this while your experiment is running. You can do multiple things at once. And when it's done, I can just say predict. And I want to predict a target column, and I can predict anything I want. Here, this last one is the default on the payment next month. So will I default on my payment or not? Can I pay my bills next month or not? And this is a credit card data set, also Kaggle from 2005, I think, from Taiwan. Every feature here has a mouse over. It also has an assistant you can click on, and then it will actually help you with every cell, explain some more what it is and all that. But basically, you just need to provide the target column. Now, sometimes you can provide a weight column if you have observation weights for every observation in a data set. Sometimes you care more about weekends or about expensive cars or people that are special status or something. And you can also provide validation data set if you wanted to make your own train test split, or train validation split, I should say. So the validation data set is what we use for model tuning. The test set is what you use at the very end to score the model to see if it's actually good or not, but we should only do that once. You shouldn't keep measuring the model's performance on the test set over and over again. Otherwise, it becomes a validation set which is used for tuning, and then you have nothing left to see if it's actually good. So we use the validation set to tune, the test set to see if it's good. Now the validation set, if you don't provide it, is cut up by us internally from the training data. And we can, like I said earlier, we can make multiple splits, and we can do a reusable holdout on that to actually measure the performance. So the numbers that you see that says how well am I doing is not just a single pass on a fixed holdout split, but it's the best guess we can do on the actual data to say this is how well we will do on similar data in the future. There is a fault column. This is for stratification. If you do something like, let's say you have 6 different people in your data set, or let's say 60 different people, but you have 100 recordings of each person. You don't want to mix up the same person into training and validation, because otherwise you learn from one signal and say, okay, I now know what this is, and then in validation you say, oh yeah, the same person, I know what the answer is, and that's a little bit cheating, right? Because you might remember the wrong thing about the person. So let's say there was a famous case where they had lung pictures, and then you had to say if that's a disease or not. And if the same person has 100 X-rays, and you put half of them into training and half into validation, then you just remember the bone structure of the person, and that says it's a sickness, right? It's not the actual image that told you it was sickness. So you want to basically split the data such that the same person is either in training or in holdout, which is validation. You do not want to mix them up. So if you have this kind of separating column, then you should provide that. And unfortunately, it's hard for us to guess which one that is, right? You can give us a CSV with 6,000 columns, and we will not know which one of those should act as a fold column. But if you don't do it, the model is junk, basically. It could be really bad, or it could be kind of okay, it depends on the data. If you don't give us a weight column, that's not so bad. That just means that your model is going to equally treat every row. And if you don't give us a validation set, that's totally fine, because we split our own way. Now, if the time matters a lot, let's say you have fall and spring, and you have a data set for each, you could provide fall for training and spring for validation, and force us to not cut up the first data set internally, but focus on training on that first one and then hold out the other one for tuning. That means select the right parameters for the pipeline such that you're doing well on this new campaign in this fall, and you train on spring. Otherwise, you're just going to get good at being good at spring, basically, and then in fall, you're going to be bad again. So validation can be provided by the user if you know there's a difference, if there's a shift. And if there is a shift, and we see that, for example, the stock price is changing dramatically, and you give this as a predictor, and that would give away the answer, because the answer is also rising, right? Like house price correlated with stock price or something, then maybe it's not the best thing to have that stock price in the data set, because that alone will tell you immediately what the house price is. So maybe you want to make a model that learns some other things than this cheater column that gives away everything because it's highly correlated. So we can detect that and say between training and validation, the stock price is changing so much, it's not a good feature, because it's not what I'm used to from training. So why should I make a model on a low stock price if all my scoring later is going to be on a high stock price? So we can automatically drop stuff like that. So it's a good idea to give a test set, basically. Yes?
Do you support real-time data, and how long does it take for the model to predict accurately, typically with the machine learning kind of solutions? It's always the data set which matters, and how much data it needs to actually accurately predict, because with few bytes or kilobytes or megabytes of data, it might not be accurate prediction.
Correct. Yeah. So the small data recipe is actually the hardest. So the question of how much data do you need? If you give us a 100-row data set, that's probably the lowest that we would consume. Otherwise, we'll just say no, it's too small. Even with 100 rows, it's not usually a good model. We do our best. We split it up in many ways, and we make repeats and all that, and we try to do the best we can to give you an estimate that's reasonable. But being a statistician will be better than being a machine learning model at 100 rows, right? So I would say thousands or tens of thousands of rows is usually the starting point for a model where you can be somewhat blind, let's say, where you don't need to know the domain too much. If you know it's a identically and independently distributed data set. So every row is same distribution as the other row. They're all just t-shirts, right, of different sizes and colors. But if they're all correlated stock prices from one day to another, then you have to have this time series nature in mind. And for that, you have to provide a time column. And then there could be other things. There could be many different groups in the time column. You could have a data set of all sales for all your people, all the Starbucks franchises, let's say, all in one data set. So if you have a gigabyte data set, all the Starbucks franchises, all the sales numbers for every person that is playing the sales role, right? So you have one data set that has the column is a date, the next column is which store, next column is which salesperson, and next column is daily sales. And now this data set you throw in and you say predict for this date, this store, this person. Tell me what's going to happen. And Driverless can do that, but it has to automatically figure out that there's these groupings by store and person. It finds these different time series, and it has to find out that it even is equally spaced in time. For example, you have every day a sales number, and if there's a weekend missing, it might be okay, but if there's too many holes in the data, then we might complain. So there's a lot of tricks and subtleties in time series forecasting, and we're trying to do more and more generalizable methods that will work in any situation. And this kind of sales per day per person thing is working very well. And we're working on other improvements, such as the ability to update the data that's inside the model so that it can make predictions far into the future on a daily basis. Let's say right now it's something like the model that we make for time series has to remember all its state from the training data. As soon as you deploy the model, you can't update the data. So it has to look back to that training period of time to make predictions for the test set. And if the test set is super long, if you're going to make predictions for 2 years, let's say, at the very end of those 2 years, you're still looking back at the training data from today, which is not a good model, right, to make predictions. You should look at yesterday's value in 2 years, right? So every day you look back at yesterday's values. And that's something we're working on to freshen up the model with fresh data, in case you have something like stock prices where every day you have fresh numbers and you can ask what was yesterday's stock price for this ticker. And that's a much better predictor than saying what was the price at the time of training. So anyway, here we have something. You can pick the score that you want. You can say I want to optimize Gini or MCC or F0.5. These are all data science specific terms. If you don't know what they mean, then you can mouse over and explains a little bit. Matthew's correlation coefficient. It looks at all the four things in the confusion matrix: false positives, false negatives, true positives, true negatives, and it will make a good model. So let's take this for fun, and let's just run with this. But you can actually change the interpretability, the accuracy, and the time you want to give it. So you can say I want a more interpretable model, I want to spend less time, and I want a super accurate, which gives you a model that uses the original features more than all these generated features that are maybe less interpretable. We'll also just do less genetic algorithm. Not much to do because the time is set to 1, and we want it to be super interpretable. So there's not much room for feature engineering, but we still want the highest accuracy. So we might do a lot of model tuning to find the best hyperparameters to make the best model on that data set. So let's look at the other model, see if it's done right now. Oh wow, 4369, that's pretty good. I almost feel tempted to submit this to Kaggle. Yeah, it's actually pretty good. Sorry, the Wi-Fi is probably a little bit slow here. Basically, the web server has to now upload all the information to my laptop. And when it's done, we can also interpret the model. So there's a full interpretation suite, and I might actually be able to show you that in the slides. So we showed this automatic visualization, and this is the interpretation. So there's a booklet that you can pick up. You should have it in the other office if it's not in this office. That talks about the interpretability of machine learning models. So if you want to make models that are interpretable, you can either turn the knob up, or you can actually look at this page to get a feel for the models. And you can say, okay, everybody who has a low outcome seems to have a high missed number of payments or something. For this credit card example, if they missed a payment the last month or the last 3 months, then it means they're not going to default. Then they're going to default. They're not going to pay on the next month, right? So you can see why do we think the model picks that up. So basically, it exposes bias in the data, if you want. It tells you what's going on in the data that leads the machine learning model to think that something is yes or no. It also gives you decision trees and partial dependence plots. So for example, you can say, what's the path where most people go down to end up with a high probability of default? Or what is the scenario, like what if scenario, if I want to like change my income, what happens? Will I be less likely to default, or will I be more likely to default? And if that's jumping around, then you know it's not a good model, right? Because the more income you have, you probably should have less chance of default, unless there's something interesting going on. So then you have to go dig deeper and see why would somebody with more income have a higher chance of default. Maybe they became more speculative, or started to gamble, or are entrepreneurs or something, and then maybe that makes sense again. So there's all these drill down methods that you can go to, and we can look at that in the GUI in a second. So it's free for a trial, 21 days, and then you can contact us to get another license key. Usually by that time people start up signing up. There's also as I mentioned, a free academic version, and support for Linux, Windows, Mac, IBM Power, RPM packages. There's also just a tar file. You can unzip it in your folder and just run it. It's like a local installer if you want, in your home directory if you're not root, if you can't install the RPM. And this for the audience that's online. On the left side are the feature engineering variables that get generated for this data set that are for IID data sets. This is not a time series problem, so this is just interactions of the columns. IID means independent and I mentioned it earlier, identically distributed. So these observations are independent of each other, and they come from the same generating function. So it's all just points from the same kind of population. And on the right side, you have a time series feature engineering. So this looks more like lags, right? The lag is a value at a prior point in time. So a lag of 1 would mean yesterday's value if my time interval is days. So for example, a lag of 52, if the unit is a week, means last year's value. So in this case, we were predicting prices or sales numbers for stores and departments. And we automatically grouped by store and department, and we knew that for a given department and store combination, last year's number is one of the most predictive numbers. Obviously, every Christmas or every Thanksgiving or so, there's more sales. Then there's another one that said, take the exponential smoothing of a certain interaction of these lags. So maybe always at Christmas and Thanksgiving, and 2 years ago also, what's the interaction of those with some exponential smoothing kernel over them. It gives you some kind of a smooth smear of those 5 numbers, and that's the best guess we have to then make a feature. And then the gradient boosting method can then say, okay, all the stores that had this number a year ago roughly, and or 2 years ago and 1 year ago, smeared over time, that number groups my stores. And when I split by that number, either I'm bigger or smaller than that number, I separate the population in a way that when I then predict their mean, it's a good prediction, right? So put all the big store sales into the right corner, all the small store sales in the left corner. Now I separated them ideally. But it's not by the sales right now, it's the sales of the past in some kind of smooth fashion over time. for each group. So every store, every department has its own time series, and we say, for each one, compute me the past exponential smoothing average, and use that as a feature. And that was the best. Then there's also cluster distances. So for example, we can take the departments and cluster them. And then you see, oh, there's departments that are like toiletry that don't have much sales because toilet paper is cheap. Then there's other departments like cosmetics that's more expensive. So you can basically group the departments. And then depending on how far you are from a certain group, that also gives away kind of what your sales gonna be, right? That is something that's interesting. Or we can do interactions of lags. You can compute the median of the sales or the maximum of the sales. It's also a good feature. Sometimes the sales are spiky, and if the maximum is no more than so and so, then you know you're not that spiky or something. It's more like this kind of store that has this kind of sales and so on. So these are all numeric features that are generated from the past. And this might give you more input than a neural net, right? A neural net will just multiply stuff and you have no idea what it actually multiplies. But this will say, okay, well, it looks like the 1 year ago value mattered a lot. So this is more interpretable by itself without doing anything. Okay, wow, that's pretty good. So 4369 is the last model here, the last point, and that's the Ensemble. So you see the model got better and better over time, the winning model of this horse race. And at the very end, we made a model that is combined of 15 models. So there's 3 different XGBoost and Light GBM models and maybe a GLM or a TensorFlow model. And so we take 3 things, and then each has 5 folds for cross-validation. That gives you 15 splits for which we fit and predict. And those 15 predicts are then done on the test set. So each one of those 15 pieces makes a predict on the test set, and then you blend them with the right weights that were also optimized using the original training data. So we have the right interaction of those 15 models, and they all have different features, all of those 15. Every one of those 15 is fitted on different data, because the 3 different model types have their own pipeline that says which features are made, and then each of the 5 folds gets a different 80% of the data, so also gets a different pipeline. So they're all fitting a different feature engineering pipeline and then a different model, and then they're making predictions on the test set that also gets transformed in the same way. So it's a super sophisticated technique that now this will be in the top 15 guaranteed at Kaggle. And I'm more than happy to do this later, upload it for those who stay around and show you that. So this just saved 2 months of time because our own grandmasters actually spent 2 months to get there in the past. This is the private leaderboard. And we get this 42999 number, which is the 10th place. And this is Dimitri Larko, who's probably sitting in the audience somewhere around the corner. He's one of the main contributors to the code that does this feature engineering. So he has automated himself, basically. And this was 2 years ago. Took him 192 submissions and 2 months of playing time, 3,000 teams, and we're now in the top 0.3% out of the box. So imagine you have your own data set somewhere. It's a good benchmark tool for sure. And it may not do this well on all problems because sometimes leakage is present in these Kaggle problems. For example, the ID, the row number matters. That's something that shouldn't matter, but it does sometimes because the data collection was such that, at a later point in time you had more events or something. So just knowing which row you are will help you predict. And sometimes Kaggle people figure that out very early on, and then they redo the whole competition, and they'll get rid of that exploitation. Sometimes they figure it out at the very end, and then it's too late to change it. So then all the grandmasters just compete at cheating the system, so to speak, to get higher accuracy, but it's useless to the business because it's actually a leak that was exploited, not an insight gained for the business, right? So often these Kaggle competitions, even with a lot of care, are not what they intended to be because of such leaks in the data. And the ability to see the whole test set, even though there's no answer in it, but you see all the data, that's already more than normal, right? In the real world, you wouldn't have next week's transactions. So this is also not a perfect match for the reality. That's why driverless does not need the test set. If you don't give us the test set, we'll still fit the same model and then make predictions just fine. You definitely do not need to give us the test set answers. That would be cheating, and we're not looking at it. Even if you give it to us, we're not going to look at it. But we might look at the distribution shift. If we know that next year's stock market is totally different than this year's, then we might drop that as a feature. So we will benefit if you give us a test set just to make sure that the distribution of the data is a good distribution. We will help you not give us a bad feature if you want. But we're not going to cheat by looking at the outcome. Okay, so let's do some, let's a little bit more about the feature engineering. So in this case, Paribas here back then, that took 19,000 features and 1,000 models. Let's see what we did today. It says here, we tried 22,000 features. So we made 22,000 columns, and we made 440 or 450 models. So we trained 450 gradient boosting models on about 20,000 features in an hour and a half, all automatically to figure out the best pipeline. Now you could say, well, that's stupid. Why don't you just build one that's really good, right? And yes, ideally we would be even faster and not build 20,000 features and just build the right ones. But in the final engineering here of the pipeline, it's still 1,000 features that we use. So those 15 models totally use 1,000 different transformations across those 15 pipelines. So they might share some, and they might have some uniques. So roughly a couple hundred or so each that are going into the models. And this data set is one where you have to look at everything, all these interactions and a long tail of features. They're all helpful. So we cannot drop. We would definitely drop, especially if you set the accuracy and interpretability differently. We will say, okay, look, this feature is not that useful, we'll drop it for you. So you can give us more features than you think you need, and we'll automatically trim it down. You can also tell us in the expert settings in the beginning how many features you want in there. You can say, I don't no more than 10 features, no more than 1,000 features, whatever it is. So we'll listen to that. We have overrides. So you can run the same experiment again. Any experiment you can restart from the last checkpoint, or you can make another model with the same parameters. And then when you say same parameters, it's preset to what you just did earlier. And now you can change it and then run again if you want to try something that's less interpretable. Or you can go to expert settings and you can switch around these buttons here. There's a lot more settings. And they're all documented. So you can say I want to make I don't need the data distribution shift, or I do want TensorFlow enabled, or I do not want light GBM, or I want to set my number of features in the pipeline to be no more than 50. Don't engineer me more than 50 features. Or don't use more than 10 original features. So you give me 1,000 wide column data set and say don't use more than 10. Right? We'll do the best we can. So there's all these options. You can also enable TensorFlow for NLP, this convolutional neural net, to change the text into a number, or not. You can turn that off if you want, because it is time consuming. It would be faster to just do TF-IDF counts. There was a question in the audience. Do we have the microphone, please?
What is the resources that you use for this particular competition? I mean, how many CPU, GPU, RAM?
So the question was, what was the CPU and GPU resource used for this experiment, for this Paribas competition? It shows it here. It says it's a Docker, Linux, a 240 gigabyte memory, 32 CPU cores, and 4 GPUs. So it was 4, most likely this is a P2, 8x large or something instance. So 32 virtual cores. So probably a 16 physical core system with hyperthreading. This is about $1 or $2 an hour, maybe I think $2 or $4 an hour. I'm not sure exactly how much. So this should be, actually it should work on CPUs too. You don't need GPUs. GPUs is very useful if you have big data. If you have like a 20 gigabyte data set and your models take 5 minutes each to fit, we'll do the best we can to shorten that time by doing a higher learning rate and all that for the genetic algorithm part. And then GPUs will make a difference of like 3x to 5x, sometimes 10x. If you don't have GPUs, you're still fine. You get insights much faster than normally if you did have to do this by hand. One thing that's also important is that the cores, the CPU cores matter. So if you have 30 cores, it's going to be really faster than if you only have 8 cores or so. So there's parallelism that we can exploit in the feature engineering, that each feature is engineered on a separate core. So it's not just about GPUs, also CPUs. Now there is a project ongoing with NVIDIA where they're trying to move everything to the GPU, including the feature engineering. And that's something that we're looking forward to, but it's not at the point yet where we can integrate right now. But it might, at some point, we might do everything on the GPU, at which point it will be faster and the memory limit will be given by the GPUs, not by the CPUs. Right now we're doing data table, which can use the main memory and all the cores of the system, so you can do big data with that. They do deep learning and, of course, non-deep learning. So deep learning is something we were part of innovating. Actually, when I joined this company 5 years ago, I was tasked to do deep learning. So I wrote the H2O deep learning package, which is widely used, and it's actually very easy to use. It runs in pure Java, so you can run this on Windows, laptops, anywhere you want, and it will do a deep learning model, which is quite accurate for these kinds of data sets. But it's not meant for images. We're not a replacement for Keras, for example, TensorFlow. We're not a tool. We just for deep learning. We're just using Keras inside of our own tool, and that's actually a pretty good idea because it's Pythonic and it is fast. So why not use that? There's no value for us to re-implement deep learning itself. Now for time series, we'll make those holdout splits internally based on time. So we'll not mix up the future and the past. We'll split it by time using causality and all that. And we'll say, okay, if your test set is in the future, how far ahead is it from the training? So if training is all the way till today and testing starts next week, we have a 1 week gap. That is how long it takes you to put the model in production, let's say. Then we can mimic that for training, and we can imitate this 1 week gap so that when the model goes to production, it will not ask for yesterday's value, but only a week ago's value, which is what you had today when you trained it. So we can basically live with the same constraints that you have. If you were to put a IoT device somewhere that has to know past values, then it has to ask for long enough ago values that were available when it was trained. But if you're a hedge fund and you always have last milliseconds values, this will not work, right? Because we are looking back to the training period of time. We're not looking back a millisecond at any given moment in the future. For that, you would have to give us the last milliseconds value, basically all the time as you score, which means you have to give us more than a single row. Currently, we only take 1 row at a time and we just predict. And that row can contain a timestamp and a store and the manager and all that, and then we tell you exactly what the sales going to be for that combination in the future. But if that model has to know every millisecond in the past, then it's not a good model to fit that in driverless today, because we don't have that last millisecond number available in test time. Because we operate on the condition that we say when the model is finished training, it gets deployed in isolation. Nobody gives us fresh data ever again. We have to be able to score in isolation. And if that's not true for you, because you actually do have every millisecond fresh data, then you need to wait for us to release the next version which will handle that. So don't run time series problems where you always have fresh data, but you run time series problems where you make a model and then you score it for a while. So let's say you have a year worth of data, and then you go to production and you score for 1 week. and then you refit a fresh one and you go again another week, right? For that kind of model, it's fine. But if you're a hedge fund that wants always the very, very frequent updates of the data, then that is not fine. So that just to let you know that you're not running it in a regime where it's not as useful. It might still be better than a RIMA model or a mean model or something, but it's not, I wouldn't be confident saying it's the best. Now, as I mentioned earlier, we do automatically detect those groups, so the store and department combinations or the salesperson or whatever that matter, that each have their own time series. We can separate those time series automatically. So we'll detect that there is 17 time series in your data set because you had 17 different stores. Now for text, you can have multiple text columns in the data set, such as tweets or descriptions or last conversation you had with the person or doctor notes or something like that. We'll tokenize it into space-separated words. So any language is fine, doesn't have to be English. We'll remove the stop words and the punctuation and so on. And then we'll do TF-IDF counts. So we'll count up how many times this word shows up here in this document versus the global the corpus of all documents in this data set. We'll say, okay, wow, this word shows up a lot here. So something is like a higher weight for that word. And then we have, let's say, 50,000 words. So we have 50,000 counts for each of those. And that's a sparse matrix, which then we have to compress down with truncated SVD, for example, to make it into 50 components. And those 50 components now are 50 columns that we use for our model as input features. So we turn the text into 50 columns. Each text field turns into 50 number fields. Another way is to take these 50,000 counts and throwing that 50,000 sparse matrix into a linear model and say, well, predict me the outcome from those zeros and ones, or counts how many times, or these relative counts. So it can be even numbers, doesn't have to be yes or no. From this sparse matrix with mostly zeros, but lots of non-zeros, those are the words that actually occur. From that matrix, you can actually predict the outcome. And that you can do out of fault, and then you have a good column, which is the likelihood given this word to get the outcome. And this likelihood is a good replacement for a string that was originally there. Then the gradient boosting models or TensorFlow models can then take that. And now you can use TensorFlow as well to make word embeddings that then take these sentences and stream them through neural net. And they have an awareness of the order of words. It's not just how many times does each word show up, but it's also is it I am rich or rich am I or something is different, right? And then you can see if the model actually learns something from these interactions in the order. And when you then have that out of fold estimate of that convolutional neural net, then that's a good replacement for a string as well. And that can then go again into another neural net. That's the actual model that takes all the other numbers and strings and so on of the data set. Or it can go into an XGBoost model or LightGBM or a GLM. So we're just turning this text into a number first and then do it. And the next step, it goes into a regular model. So we're just getting rid of the text if you want. And once that's done, one time, we cache it. So once the text is converted to these numbers, we can use that feature from now on instead of the text. So we're not, for every experiment, every yellow dot on the plot, we don't have to redo this. We just have to do it for every split in the cross-validation folds. But we don't have to do it for every single fit of a model. All right, so and in the end, of course, you get documentation that tells you what happened. So there's a full PDF coming out telling you, okay, we did 5-fold, this and that, we need these features, these are the top features, this is the description of all the features, this is the pipeline that came out, this many models, this many features, and this is how well it does. So there's all these metrics, Gini, MCC, F1 and so on, accuracy, log loss, AOCs. Each has an error bar, has a number for the training data, internal validation splits for the test set data. And if you have an external validation set, that's also possible to see. So there's all these numbers. And we're working on making it more visible in the GUI, all these metrics, so you can actually compare different models on different data sets and see which one has what ROC curve, what's the difference. And we want to also add more model debugging tools. That's all for the roadmap for the next few months. And there's also going to be new models, such as FTRL, which is a streaming algorithm similar to a linear model. Like stochastic gradient descent linear model would be the closest. So you take one row at a time and you make a prediction with a linear model. Anything that's wrong fixes your current weights for each of the predictors. So how many times age plus how many times income plus how many times zip code gives the right answer, basically. You correct those weights until you get a good model. Now, FTRL will do the same thing. We'll do it multi-threaded. It will do it with higher order interactions. So the weight is not just for age and income and zip code, but the weight is for age times income or age times zip code, let's say. But there's also an ability to handle strings. So if you have a word like hello world, then that's also a coefficient that it gets. So how many times hello world? How many times this URL? How many times this marriage or single coefficient? And of course, if the URL shows up only 6 times in the whole data set, then the weight might be relatively small because it didn't matter too much. But if the word is male or female, then it has a more important number because every single row will fix that number until it's correct, right? So then you get a big number, like a 0.3 times gender or whatever it is. And then who knows if it helps or not, but it's a linear model that has a weight for male and has a weight for female in the linear coefficients. And you can have then a weight for male times age, and then different age groups have different bins, and for each of those male times different age groups or female times different age group, there's a separate coefficient. And if you're in that age group, then that coefficient is applied. If you're not in that age group, you get a 0. So for everybody in the room here, there will be a coefficient that says how much is their contribution to your default likelihood, right? And all these coefficients are automatically trained in parallel, fast, in a streaming fashion, so it uses no memory at all other than to store the coefficients. And you can throw a terabyte data set at it, and it'll just stream through it, and in the end you get these coefficients. So that's FTRL. That's similar to deep learning, except that the weights are clearly defined for those interactions. So it's not like a deep neural net, it's like a one-layer neural net, if you want. But we can do it very fast because it's using a hashing trick to turn the strings into an index for which we have a weight. So it's a long weight vector that's indexed by the hash function outcome applied to the input. Whether it's a number or a string doesn't matter. Whatever you throw at it as a feature, it hashes it into an integer, does a modulo on it, and that's the vector entry that you're changing with the update method. That's a pretty cool algorithm. That's what Google used for their AdSense. And soon that will be available in driverless. So let's see if we have here the demo. So I want to go to the credit card data set. And here I'm going to interpret this one. So what we have here is the machine learning interpretability module that will show us for every row in the data set why we made that prediction. So you can get a feel for how the model operates and what's the thinking behind the decisions. And sometimes you'll see that, oh wow, there's the ID mattered a lot or something, and then you should have dropped the ID. Now we automatically drop IDs, but if you somehow sneak in something that looks like an ID but not quite or something, and it remains in there and it's super predictable, you get an AOC of 1, then you know why, basically. This will tell you. The feature importance listing in the first page also will show you a very high importance, which means you probably overfit that feature. Something is wrong with that feature. Now we will not overfit, but we will say, wow, this is a very predictive feature. And you should then decide, is that actually a good thing or not? Is that actually true that that feature is so predictive? Or is it just me making a bad data set? So do you want to go to the MLI page? Yes. MLI is machine learning interpretability. So this now says, okay, we did this model. It took 52 seconds, and we built actually here a bunch of surrogate models and clusters. So let me go to the dashboard. That's usually the easiest way to start. So the dashboard shows you the four different things. So one of the things is, let me get rid of this X here, the top left chart. So what it does is it sorts all the predictions and the actual values of the data set. So it has all the zeros and ones. So there's two lines, all the zeros on the bottom, all the ones on top. And it sorts them by prediction. So there's a yellow line going from the left bottom all the way up to the right top. So it sorts all the points by what we think is the default probability. Now the guys on the right should be really more yeses, and the guys on the left should be more no's if we had a good model. And that seems to be the case, so that the yellow dot density at the top right is higher and the yellow dot density on the left bottom is high. But what you also see is these sprayed in white dots, and those are a prediction of a approximate model that's a linear model. So instead of doing our ensemble of XGBoosts and light GBMs and TensorFlows, we now have a linear model that only has a bunch of coefficients, and it comes up with roughly the same answer because it's following this yellow line. So for the points that are high here, you have also high numbers predicted by the linear model. So these were 15 different clusters that we found in the data, and then for each of those 15 clusters we fitted a linear model. And that is basically the model of those who default a lot, and then here is a different model for those that don't default, right? And each one has its reasons basically, and these are reason codes. These are just the beta times X values. So if you have, that basically adds up to the final number along the X-axis, and then it goes up the sigmoid function and then becomes a probability. So the more the number, the more we go right. Or if you add a negative contribution, you go back left. So the more right you go, the higher probability, the more left you go, the smaller probability. And these numbers are basically telling you how much they add to the overall probability. So there's kind of a reason code that you can say, okay, P0 added this much to the probability. Now, if you pick a point, then we will get feature importances for this point. So the gray bars are now showing up, which is the importance of the features for this specific point. So you can actually see, compared to everybody else, I have a higher importance to pay 2. And pay 2 is saying, did I pay last month? Pay 0 means, or actually 2 months ago. Pay 0 means the last time I was able, I should have paid, did I pay or not? So pay 0 matters the most. The most recent time I should have paid my bill, did I pay or not? Pay 2 says the previous time, did I pay or not? Pay 3 says, again, previous time, right? And now you see pay 5 and pay 4 are mixed up here. So the model thought that pay 5 mattered slightly more than pay 4, even though it was further ago. So maybe that's just an artifact of the small data. It's 24,000 rows only. You would think that further ago means like less important, and closer to time means more important. So this is some insight we can get here, that the data signal is not super strong. There's partial dependence plot. So let's say if I pay more 3 months ago, what happens with my outcome, right? And it's just statistics. It will show you if I change my number and I predict, what do I get out? So is my model sensitive to that change or not? And it gives you kind of a what-if scenario. Now, it's not quite right, because if you actually had a higher pay 3, it wouldn't be the same point anymore. So then the rest of the model might not have applied either. So the model never saw that kind of point. So why should it be good at predicting for it, right? If you change it too much, you make it artificial, and the model never saw those kinds of artificial points. So how can it predict for those? It's hard to extrapolate outside of what it saw too much, but maybe a little bit you can get a feel for it. can also download these reason codes and scoring pipelines. All this stuff can run outside of driverless in Python. There's a lot of other things that you can do. You can do Shapley values, which is exact contribution to that x value I mentioned earlier before you go up the logistic function. So you can see for a given point, the contribution of pay amount 6 was this much. It actually made my probability slightly less. And pay 0 or pay 3 and pay 2 made it much more. So pay 2 made it much worse, my likelihood that I would default. It added a big positive contribution going right on the x-axis, which increases my probability. So these are additive terms here. If you add up those gray bars, the pluses and the minuses, you get to some point on the x-axis, and then you have to go up the logistic function, that's your probability. So it's super easy to understand these contributions. And this contribution is from a random forest here. Now, that's from a surrogate model, but you can also do it on the actual model. Our actual model also had these Shapley contributions. So you can ask our full ensemble, what's the contribution of this particular feature to the final outcome probability. Now, it's the random forest number for Shapley here, loco, had the original features, the ones that you gave us, contributions. Now, this one here has the features that were transformed by us, because we first, as I said, we first enrich the data and then we give it to the XGBoost. So it only sees those XGBoost models, they only see transformed features. So here you get a list of transformed features. Now, because I set the interpretability very high, I kept them the same here. So now we have actual impact of the original features into our tuned models. So this is probably the most useful one here, because it's telling you exactly what's the contribution to my one, for this particular row, 11,197, how much did this feature contribute to the outcome? And this is our original feature, because we didn't transform it in this model. But of course, if your original feature is a text field, we do have to transform it somehow. At that point, it becomes more complicated. And then it would say it's the CNN's likelihood encoding of the text for this guy. And then you have to go look up this guy's text and say, oh wow, because the text was such and such means it's this high probability. So you have to go back a little bit for those cases. But we could make it easier for you to highlight the original features for this row. So any feedback you would have, I would love to hear. So now that we have this model, we can download this automatic report that is being built. So there's other buttons here. We did interpret. Now we can score on another data set. So you can give another test set and score on it. You can also give another data set, and we can transform it as if it was basically as if you wanted to see the inside of our feature engineering. Then we'll spit out a feature engineered version of that data set. Then you can say, I want to download the Python scoring pipeline, the thing that is standalone, or I want to make a Mojo version, which is the Java version of that scoring pipeline. So I just built it. Now we can download it. And if you open this Mojo one, it actually has a jar file. See, it's a pure Java standalone scoring pipeline. And then you can download the experiment summary and the logs. The experiment summary has a bunch of files in it. It has text files and JSON files. So these are pandas frames, that's JSON, so you can import them in other tools. They will show you all the features. For example, what are the importances of all the different features? What are the different parameter tuning tables? So you can see what different models were tried, XGBoost and so on, how well are they doing. This is a full leaderboard with hundreds of models, and you can exactly see how they're doing. And you can of course turn that into a pandas frame with this JSON, so you can quickly look at that in a Jupyter notebook, do whatever you want with it. And there's a report PDF, which is the AutoDoc report I mentioned earlier. So this for regulatory use, you can. This is also given to you as a markdown file, so you can actually change it and then modify it if you want to write text to it and say this is what I did, this is why I did it. And we're working with banks to customize those reports so that they can have their own version of the report that they want. And it will tell you how many models were built for each phase and what the parameters were and so on. And by the way, if you're interested in how driverless AI was built, you can go to blog.h2o.ai, and there is a full blog on the making of driverless AI, which is going into much more detail about the history of the product and how we originally started thinking about it, how the different pieces such as data table or MLI were conceptualized and then implemented, the GPU algorithms, collaboration with NVIDIA, the Kaggle Grandmaster ideas, the overall application stack, the GUI, how it was first designed, how it came together, automatic visualization, and then the first Kaggle results that were promising, the booklets that were made, the architecture, and then all the different features that were added in rapid succession, and the time series thinking behind the whole recipe, and then also the TensorFlow text stuff that I mentioned. And there was a whole conference in London last month where we gave a lot of presentations, lots of customers talked about it, so there's lots of good information here. Kaggle Grandmaster panel, all the videos on YouTube, everything's public, you can look at it. And then the future, this is the roadmap that I'm going to talk about. So the integration of the H2O-3 platform with driverless AI, this convergence is happening now. So you might want to, for example, create a good H2O-3 model using driverless. So driverless can tell you what to do, and then H2O-3 will do it on a terabyte on a sparkling water cluster, for example. This is a good idea, and we will do that. Another idea is to say, now that I have a driverless model, Mojo, the standalone Java scoring, can I put that into sparkling water and then score on a terabyte to make faster predictions than throwing it through a single-threaded scorer here? Can I use my cluster as a scoring mechanism? Or can I just, for example, can I train driverless from inside of the open source product? In the open source product, you might want to have a button that says fit driverless on this data set. And if you have driverless running, then you can just connect to it, and it will make you another H2O-3 model, because it can produce that Mojo artifact outside and then suck it into Java and just score, right? We have all the pieces in place, we just have to wire it up. So we can make a call out, say fit the driverless model, give me the Mojo back, stick it into the Java MapReduce, and have a parallel scoring engine that then acts like an H2O-3 model for which you can make metrics, you can score it, you can call it from R and Python, you can deploy it as a Mojo, and so on. This is a very natural interaction between the two platforms. We will make a multi-node, multi-user version. This is already multi-user, but not multi-node yet. So there will be more scalability, more people can run experiments, they can share experiments, they will be able to score the models on different data sets, see how it's doing. There will be new scoring tools such as the C++ runtime, not just Java. So if you want to have TensorFlow models, that will come in February for our next H2O World in San Francisco, for which you should sign up if you're interested in these developments. And then there's also going to be more debugging tools where we can actually see the things like residual analysis and so on, see why the models are doing wrongly at certain points, and then see what's driving those mistakes and so on. And the thing that I like also is the manual fine control. So let's say you have a pipeline that comes out that says this is really a good feature engineering pipeline, and you look at it and you say, no, it should not be doing age minus zip code. That's a bad feature. It doesn't make sense. But we automatically figure that out as a useful feature. You should be able to like exit out and say go away, right? So this kind of final manual inspection of your pipeline, where you can mess around with that state and say, no, add this feature, age plus income is actually good, but not age minus income or something. You can just play with it and say, now submit and fit the model again. So this is also on the roadmap, to be able to control your final model. And so we make a guess and then you approve it, so to speak. That way you have more control. Right now your only control is which buttons to press and what data to give us, which is still nice because you don't have to worry about the hyperparameter tuning and the feature engineering. But sometimes you do care about the features that are being engineered so that you can explain it to the end user. And sometimes it's useful for you to say, everything that happens here I can vouch for, and not just some black box, right? So we definitely want to make that better. Here are some links. So if there's any questions, now would be a good time, I think. If I forgot anything, I will be more than happy to go back and show you that. There's a question here. Can you bring the mic, please? Thanks.
So for the time series models, do you do multiple time series and correlation across them? Or is it a single time series?
So for every group, we say there's one time series, right? So let's say you have a store and a department, and then you have 2 years of data. That is to us one line.
Yeah, that's one line, but you might have like a time series for two different like sensors, and you want to see the correlation between
Yes.
them.
Yes, so that's a good point. Yes, exactly. So that's actually what's happening, because in one data set we have all the different time series, right? So they're all the different groups and stores, or let's say sensors, they all have their own time series. So for every date there is a sensor ID.
Yeah.
So you have 1,000 times the same date for all of the 1,000 sensors. Each one has a value. So let's say today,
Or staggered.
yeah, however they're ordered doesn't matter, but they have like a date stamp and the sensor ID, and then you have a value. And then for the same day you have 1,000 rows, right? Where they all have same day, different sensor, different value. And the next day, 1,000 different IDs for sensors, different value, and so on. You have this for 10 years. So now we have actually 1,000 time series going on, and we can make lag features for all of them at once after we do some grouping in the data table. And then those 1,000 time series are all at once. So it's one time series per group, but the data set has actually all 1,000 in it. And then when XGBoost looks at them, of course, they look at all the interactions. So you can actually see if sensor ID is 17 and 6 months ago's value was 5, and then sensor ID is so and so, and 5 months ago was this and this, then group them together with a split in XGBoost, for example. So yes, definitely they do interact. That's one of the strengths of this recipe, is that we don't make 1,000 ARIMA models, but we have one massive model that looks at all the data together. Yeah.
So what was after is slightly different thing. So I understand that you're collapsing these models into creating model per group. Because I really want to see that if something happens in the first time series, maybe with a lag, something will happen in the second time series. They're really independent of each other. You do it in the stock market all the time, right? You know, if this stock moves, then the other stock going to move maybe later, so you want to predict that.
Yeah, we do have the lags for all the different groups, and we have the lags for the other groups. Yes, yes.
Yeah, it's that type of correlation. The secret sauce in Wall Street.
But I think it should be presented to the algo already, because you do have all the lags for all the different stocks at once, and you can present that to XGBoost, let's say, and it can say if I split them properly, that will happen. But you have to maybe make ratios and not just values. So it's stuff like that. That's the next level secret sauce. Or you don't want to just predict the value, you want to predict the change of value, and maybe you want to have ratios of changes from the past between different lags and so on. And these are interrelations between lags and groups. Yeah. So we do between lags for the same group. So we can say, for example, the ratio of a year ago and 2 years ago, yes, the autocorrelation part, but the cross correlation to other groups at the same lag, let's say, or different lags, that could happen only as an XGBoost effect, not intentionally by us directly, yes. But if you had a neural net as a main model here, then that's what we have. Then the neural net could do more than just simple if-else, so it could come up with that. But it's not, we don't materialize that feature as an extra feature. Yeah.
But it quickly runs out of memory, that's the problem.
Yes, yes. Especially as LSTMs, yeah, if you have a lot of windows.
Densify it and do it, because it can't handle the sparseness.
Yes, yes, you have to pad it all.
So then that densification blows up the
Mm-hmm.
amount of memory you need. But
Even the 32 gig voltas aren't enough anymore if you do densification of time series for small
densification causes
small millisecond latencies and so on. Yeah, yeah. Any other questions? One thing I didn't mention was the time series MLI also shows you the actual and predicted against each other. So there's a time series visualization of the actual outcome. So it's a nice feature. You can see where you're doing how well. And for each group, so for each store, you can see the predicted versus actual plotted in the GUI. And you can also click on any point in time and it will tell you why it made those time series predictions. So you can say it's because of this feature. So we have this whole Shapley importances for time series for each group in a visual way as well. Cool, thanks a lot for your attention and hope to hear more from you. Feedback, thanks.